We're going to talk about applications of, algebra, of simple linear algebra equations. So this would be kind of the word problem stuff. I would say in general, how many people just get a little bit nervous when they hear the phrase word problem or story problem? Does that make you a little, well, that's good. That's good. Maybe a few. It shouldn't. There's one thing I've noticed in teaching all these years is that the word problems or the story problems or the applications, whatever you want to call them, the part that takes practice is the translation part into math, right? Translating the words into math. But once you get there, typically the problems that you solve are easier math problems than the ones that are just pure abstract math. So there's the good news. But what we need to practice a little bit is just this idea of applying a problem-solving strategy that's going to get us into algebra mode where we can kind of just focus on the math and then back into interpreting our answer, all right? This is, say maybe just a couple quick things about this. I think math is beautiful in its own right, and we'll talk a little bit about that soon. But my background, I wasn't a math major in college. I was a physics major, but physics involves math, lots and lots of math. And so the math that I focused on was more applied, right? So it was about solving physics problems. And so I think this stuff is important. Being able to apply math to solve problems is primarily what we do with math. So it's worth getting used to. I will say you can't really do anything yet that's very substantial because you don't really know enough math. But you start to see that in a couple of years when you get into calculus, you start to see, okay, now all of a sudden just the world opens up and you can start to solve some problems that are really very meaningful. But until you get there, honestly, trying to do too much application, I think, is a little bit putting the cart before the horse because you just don't know enough math yet to do anything really, really cool. But you're getting there. It's getting closer and closer, so hang in there. Just wait till you get to calculus. Calculus is awesome. So what are we going to do? We're going to write algebraic expressions that can be simplified, and we're going to apply some steps to solving problems. Now let's just kind of take a quick look at a general strategy, and it's going to look different for every individual application problem. But this is sort of the skeleton or the framework that we'll apply. What's the first thing we do? Well, we want to understand the problem. You want to become comfortable with the problem. You want to read through it, maybe reread through it. Think about a solution and check your thoughts. Pay careful attention to how you check your proposed solution. If you're solving an equation, the algebra part is easy to check. You just plug your solutions back into the algebra and see if it worked. But there's still the part where you have to determine, is the algebra that you developed consistent with the problem? So there's a little bit to this. This step right here sometimes gets skipped over too quickly. People want to, and it's because you're advanced students, you're really intelligent, you're overachievers, you want to get to an answer. But sometimes jumping into a problem before you're really prepared is actually a waste of time because you go down the wrong path. I'll tell a story. I know my son's an engineering student in college, and his freshman year, when he got into some pretty tough math classes, and one of his math classes, he literally had to sit there and stare at a problem for 3 hours without writing anything down, just thinking about it until finally, it's just like he came up with a potential path for a solution, and it ended up working. But I'm not suggesting that's going to happen to you guys this year a bunch, but you got to give yourself a little time. You got to let your brain subconsciously kind of do its thing, and before you know it, a lot of times you'll surprise yourself, and you will come up with a path to a solution, even though it seemed like it might have been impossible at first. You got to slow down and let your mind do its thing. So don't underestimate that first part. Understand the problem. Step 2, translate the problem into algebra, typically an equation, right? That's the part that we're going to probably practice the most. Part 3, I would call this just flipping it into algebra mode and going to work. This is the easy part for you guys. You're good math students. So once you get down to the point where you can just do algebra, you can just put it in cruise control and do the algebra. And then finally, when you're done with that, you've got to interpret that answer in the context of the original question. So you get your mathematical solutions. Now, how do they apply to the original question that was being asked? So let's look at a couple just examples here. So what about something like this? A new television set was recently purchased for the common room in a residence hall for $449.40, including tax. If the tax is 7%, find the price of the television set before taxes. Okay, how could we tackle this? What do you think? Some ideas. One other thing that's oftentimes very helpful is to just define any variables. And the variables are typically the things that are being asked about, right? So if we let the variable be x, the unknown, variable and unknown are kind of interchangeable ideas here. What is it that we're trying to find the value of? Okay, so x is the original price or the price before tax, right? Let's write that down. Okay? Let you think about that for a second. Any suggestions? How do you calculate the tax on something? But we don't live in a sales tax state, so you guys are at a little bit of a disadvantage, but you shop in Tri-Cities, right? How do you calculate tax? If there's a 5% sales tax, for example, how would you calculate how much tax is being charged? So what does that look like? Multiply 0.05 times the purchase price. Good. So if it was an $80 item, then you just multiply 80 times 0.05, and that's going to give you the amount of sales tax that you're paying, right? Okay. So ideas. How could we set this up then? Okay, so here's a suggestion, and we got to start somewhere. So let's start with this, and then we'll go from here. So the idea is 449.40 divided by 7%, which would be 0.07 equals x. Okay, if we do that, let's just think about this. If I divide 449.4 by 0.07, what kind of a number am I going to get? A really big number, yeah, okay. So now we're looking for the price before taxes. Should that be greater than or less than 449.40? Should be less than, right? Because this is the 449.40 is the price including the extra tax, right? Okay, so it was an idea. But maybe we'll backtrack on that one a little bit. What do you think?
Could we try 0.07 multiplied by x equals 449?
Okay, let's try that. Let's try that. So we'll go 0.07x equals 449.40, like that. Okay, isn't that going to give us the very same thing though? That's one step away from this. It's close. You're on the right track. We got to just tweak it a little bit. What do you think?
Multiply 449.4 by 0.07
So,
to get, multiply the two numbers to get the 7% of 449.4, and then you can subtract that.
okay. So the idea is, next idea, and I'm gonna erase this just because it really just led to that previous step. And this is the way math works a lot of times. You try things out, and then you just, until in your brain slowly is kind of focusing in on something that's going to work. So this idea was to multiply 0.07 times 449.40 to see what the amount of the sales tax was. Is that the idea? Okay, that's going to give us something pretty small that might seem reasonable. Does anybody see a little problem with that though? What do you think? Okay, yeah, we're multiplying 7% times the price after tax. What do we need to multiply it by? The price before tax, huh? What's that? What's the price before tax? That's X. There you go, right? Does that make sense? Okay, so what we really want to do is we want to do something similar to that. But we want to multiply X by 7%. Now, what's that going to give us? Okay, so is that going to be, describe that amount though. What does that amount represent?
Would we take the 0.07x and subtract it from 4.0?
Okay, right. So we could take that and subtract it from, because what this represents 7% of the original pre-tax price, agreed? So isn't this the extra amount of money that we're paying in tax? Everybody agree? Okay. So we could subtract that from 449.40, or another way to think about it is, what would happen if we added that to the original pre-tax price? What should all of that equal? 440. Does that make sense? That should equal the 449.40. Right? The original price plus the additional tax amount equals the price after tax. Everybody see that? Okay. Give me 1 to 5 on that. How we doing? Okay. So what would probably our next step be here? What do you think? Combine like terms. Yeah, what's 0.07x plus x? Okay, now, and let's think about that statement, because this might have been a reasonable starting place. 1.07x equals 449.40. I would argue that that could have been our first step. How come? How could you start there? Say it again.
You're paying 107.
Exactly. If I'm paying the original price, what percentage of the pre-tax price was there before tax? 100%, right? You're paying 100% of the pre-tax price plus an additional 7%, which means after tax you're paying 107% of what you would have paid if there were no tax. Everybody get that? Okay. So that's a great place to start. And then all I have to do now is just divide each side by x. And what do we get here? Well, I don't know. I don't know what that's going to be. Somebody crank that out on your calculator or on your, just open up Desmos Scientific and let me know what we get. Or actually, yeah, here, I can just do it. Unless you beat me to it. Oops. 420. Okay. So there we go, right? Okay, now, does that seem reasonable? It's always good to just ask yourself, okay, does that seem like that passes the reasonableness test? Seems pretty reasonable, doesn't it? It's a little bit less than the final purchase price because we paid some additional tax. I mean, it seems like it's in the ballpark. So, yeah. Okay, how do we feel about that? Okay, and that's what we were looking for. So in this case, the algebra solution corresponds exactly to what it is we're trying to find. Oh, I guess we can check ourselves. What did we get? Hey, what do you know? We got it. Okay? Questions? Anything about that seem unclear? Okay? The days are gone, pretty much, when there was just one little recipe you could always follow. Math starts to get more open-ended when you get into higher level math classes. And so every problem is going to be a little bit different, which makes it a lot more fun. Okay, how about this one? One number is 7 times a first number. Okay, so we're just going to distinguish the numbers. There's 3 numbers. We'll call them first number, second number, third number to keep them separate. A third number is 100 more than the first number. Write an expression for the sum of the numbers. Okay. Can't do that. Good. Okay, the first number needs to be x. How come it's the first number that we would call x, or whatever we're going to choose for our variable? Usually x. Okay, because the other numbers are, we are described in terms of the first number, right? They're always referencing the first number. So the one that we know nothing about, that we have no additional information about, has to be the one that we call our unknown, x, right? Give me 1 to 5 on that. Does that make sense? Okay, and that helps. Just even recognizing that starting place is really helpful. Okay, so first number is x. What does this tell us? Okay, second number is 7x. And the third number, okay, so we want to write an expression for the sum of the numbers. What would that be? Plus, which equals, good. Okay, no big deal. Now, what if the problem were just a little bit bigger? They're telling us same information, but they want to know if the sum of the three numbers is 757, find the numbers. So what would I do? If the sum is 757, what's that give us? I think I heard it. It gives us an equation, right? If we're asked to find something, find implies I'm solving, right? I'm solving for something. In order to solve for something, I must have an equation or a system of equations or something like that, right? So we get an equation. Good. If the sum is 757, then we get the equation 9x plus 100 equals 757. Okay, I mean, that's pretty easy to solve, right? We just isolate the x, subtract 100. We divide by 9. And what are we going to get? 79 for x. Are we done? 79? Oh, was it 73? Oh, whoops, 73, sorry. Are we done? 73? Not really, right? Now you're still in algebra mode. You got to shift out of algebra mode and shift back to application mode. What was this really asking about? Each of the numbers. Okay, so if x is 73, what is that telling us? First number is 73. What's the second number going to be? 511. Good. If we multiply that by 7. And the last number? There we go. And we could check, I guess by just adding those up to see if they do what they're supposed to do. And they do. Okay? Make sense? All right. Okay, what about one like this, like a geometry problem? The length of one base of a trapezoid is 19 less than 5 times the length of the other base. If the trapezoid has a height of 18 and an area of 477 in our units or feet, in square feet, find the length of the longer base. Okay? Where do I start? If it's a geometry problem, I probably need to start with maybe a picture, right? Always, when you can, drawing a diagram or a picture is generally very, very helpful, right? So let's do that. So what's a trapezoid look like from last year? What's the definition of a trapezoid? Okay, it's got one pair of parallel sides, right? And it's quadrilateral, right? Four-sided figure. So something like this. something kind of like that, maybe. Okay, it tells us the length of one base of a trapezoid is 19 less than 5 times the length of the other base. Okay, we don't know which one is which, but I got to call one of these x. It's unknown. Agreed? The height we know. What is the height? 18. So we know this distance is 18. I'm just going to call that one x arbitrarily. Okay? So if that one's x, what's the other one? 5x minus 19. Good, and we get that here, don't we? The length of one base is 19 less than 5 times the other base. So that's giving us 5x minus 19. Okay, what's the formula for the area of a trapezoid? Do you remember? Probably not. But don't bother. Don't waste brain cells memorizing stuff. That's the lowest possible level learning. It just goes away. Instead, just derive this for yourself. You can do this. How could I, what's helpful in geometry sometimes, well, oftentimes, is to just play a little animation game in your mind. Is there a way that you could reconfigure that area to make it something much easier to calculate? Anybody see a trick? What are the easiest areas to calculate in geometry? Squares or rectangles more generally, right? Very simple. Would there be a way to turn this into a rectangle? What would I do? Okay, yeah, if I took the midpoint of that side and I cut that piece off right there and placed it at the top, everybody see what that would do? Okay, same thing over here. I end up with a rectangle with a height of 18. What's going to be the length of each side? What's it going to be? Yeah, what I do, so if the amount that I took off of this one, I added to that one, right? Everybody agree? Okay. The sum of the two bases is still going to be the same. I didn't change the sum of the two, agreed? In other words, if an ant were to walk across the top of this shape and then walk across the bottom, he's going to walk the same total distance if he's walking on the trapezoid or the rectangle, right? So in the case of the rectangle, all we did is we split that total length equally among the two bases instead of having it, one be large and one be small, agreed? So what would I do to the sum of the two bases then to find the length of each side of the rectangle, each base of the rectangle, we're going to call it? The total would be 6x minus 19 if I add them up, right? So I just divide by 2 because we're splitting it equally, right? I just average the two. Everybody agree? So this would just be 6x minus 19 over 2 would just be that length, right? And in general, if I called this like B1 and B2, haven't I just added, I've just averaged the two bases. I added up the bases and divided by 2. So in general, the area of a trapezoid is just going to equal the sum of the bases divided by 2 times the height. You're probably used to seeing that as a 1/2 the height times B1 plus B2 or something, but same thing, right? Okay. See how we can do that stuff without needing formulas a lot of times? We can just derive them for ourselves real quick. That's what I do all the time. I rarely try to remember stuff. Okay, so now what? We know the total area by this formula. That's just going to be 6x minus 19 over 2 times what? 18. And what should that equal? 477. Well, I could simplify 18 divided by 2 is just 9, right? I could reduce that fraction. So 9 times the quantity 6x minus 19 equals 477. Okay, so let's use inverse operations to isolate x. What should I do first? Okay, I could, but that's not what inverse operations tells me to do. Yeah, divide. How come? Let's look at PEMDAS. Oops, we're isolating, so we're going that direction, right? Bottom to top. I can point to a single x, therefore I can isolate it with inverse operations. What's it tell me first? I got to do everything, well, starting at the bottom, I'm working outside of parentheses first, and you guys get that, I'm sure. So I wouldn't add 19 first because that's stuck inside the parentheses, which I don't get to until the top, right? So what's first then? Well, add or subtract outside of parentheses. Is there any addition or subtraction necessary outside of parentheses? No, we skipped through that step. The first thing we would need to do is undo multiplication with division. So I divide each side by 9, giving me 6x minus 19 equals 53. Now what? Last two steps in order. Add 19 and then divide by 6. Okay, so 6x equals 72. So what's x? That's supposed to be a 7. 12, there you go. Okay, we done? We solved the algebra, we done? No, we got to get out of algebra mode, go back to application mode. What are they asking for? The length of the longer base. Well, that means this guy's going to be 12, right? This one's going to be longer. What's the other base going to be? 41, right? 5 times 12 minus 19 is 41, so that's our answer, okay? I guess we're right here. Find the length of the longer base, 41 feet, okay? Give me thumbs, up, down, sideways. How are we doing there? Good on that? Okay? Oh, I'm not going to do this one. I'm going to put this, put this in the notes if you want to look at it. Here's another example. But I'm not going to spend time on that one. Let's look at a couple percentage ones, because it seems like those are the things people, if they haven't done it in a while, they have the toughest time. Let's look at A. What number is 45% of 84? So the unknown is the number that is 45% of 84. How could I set that up as an equation? 0.45 equals the unknown in this case, right? I don't have to do any algebra at all, do I? Yeah, look at that. This is one where what number, so that's x, right? That's what we're looking for is, well, they call it n, is equals 45% of 84 is just, how do we take 45% of a number? Well, you just multiply the number by 0.045. You guys told me that earlier, okay? So there's our equation. N is already isolated. All we have to do is just plug and chug, right? Plug in, well, we don't have to even do that. We just crank through the arithmetic, and we get 37.8. Okay, make sense? Does that make sense? Seems about right, doesn't it? Okay, compare that to problem C. 168 is what percent of 112? 168 is what percent of 112? Is your answer, tell me something about your answer here. It's going to be over 100, isn't it? Right? Because 168 is more than 112, so it has to be more than 100% of 112. So how come my variable is the percentage in this case, right? Okay. So how could I set this up? 168 is, so what's that? Equals, 168 equals what percent? Well, we'd probably call it x, but they're calling it p times 112. Make sense? When we say a percentage of, we're just multiplying a decimal times something, which again, you told me a while ago. So what's the one algebra step? Divide both sides by 112. And if we do that, we get 1.5. So 1.5%? Ah, good. We got to convert that to percentage, don't we? So 150. Yep, there you go. Okay, good. Give me thumbs. How we doing? Good? All right. Okay, the label on Audrey's yogurt said that one serving provided 12 grams of protein, which is 24% of the recommended daily amount. What is the total recommended daily amount of protein? So our unknown is the recommended daily amount, right? Call that X. Or whatever our variable is going to be. How would we set that up?
0.24x equals 12.
Okay, right. So 12 grams is, so 12 equals 24% of, right? If we turn all this stuff into words, 12 grams is 12 equals 24% of, oh man, is it not? There we go. 24% of daily recommended amount, 0.24x, and those things must be equal. They let it be A, okay, instead of X, but that's what we get. 12 equals 0.024 times our unknown, A. Divide each side by 0.24, and I get 50. Does that make sense? Does that seem reasonable? Yeah, I think so. If 12 grams is 24% of the recommended daily amount, the recommended daily amount must be roughly 4 times. That's right. Roughly 4 times 12 would be 40. Yeah, it seems about right, doesn't it? Okay, good. Okay, does this make sense? Yeah, it makes sense. Okay, I think that's, I mean, we could do more and more of these, but I think it's just time just to jump in and practice. You just got to just get some practice on these. How much time we got?
7 minutes.
7 minutes, up to you. If you maybe you can get a problem done, do what you can.